I knew replacing this backbox was going to be a big project, but I never expected it was going to be a feature-length trilogy. Hello everybody, I'm Ellie Mechanical. We left off the last video with a promise that the transfer of hardware and electronics was going to be an entire project, and you better believe it really is. Now, I will admit, I did this to myself. Not just wrecking the game in the first place, but making the repair unnecessarily complicated. I didn't have to go all graphic designer, I didn't have to seal the edges with resin, and I certainly didn't have to do anything special with the lighted insert panel beyond transferring it straight over. But I did tell you I was crazy. This is the backbox insert panel of a typical Williams game. It's a 1/2-inch thick piece of MDF with a bunch of tiny lamp sockets poking through it. In those sockets are a bunch of incandescent bulbs, bayonet base, numbered 44 for the originals or 47 for a common, slightly cooler but dimmer replacement. And like many older games that survived into the modern age, this one has the bulbs swapped out for LED equivalents. Warm white, because I have taste. That solution works decently well on the surface level, but one disadvantage of LEDs is that since they aren't based on a hot filament, they lose their smooth fade on and off. Some modern games make use of this instant on, instant off and the other capabilities of LEDs, but a game from 1989 was never designed for that, and it made flashing effects unnecessarily jarring. And so, we're about to embark on a project to modernize this game's lighting, and we're going to do that by tearing out some of the original parts and replacing them with versions that work the way I want them to. Oh god, that's what Nightmare did.
I'm going to upgrade the lighting.
But an LED strip wouldn't work with the existing electronics.
Give me that soldering iron.
Now, despite the world's rampant consumerism, I don't believe there's a product that does exactly what we're looking for already. We want consistent lighting across the backglass, slow changes in brightness as it turns on and off, and it also has to run only on the power available at the relay. GIOCD exists, but it doesn't appear to be available for the System 11 platform or work with these LED strips. So I sat down in terrible video lighting, I will admit fault, and began planning out a frame to hold that LED strip. This began with some photos of the light positions and electronic obstacles in the existing box, and a bit of work in the free retouching editor GIMP to make myself a base to work from. So I'm going to make this a little bit less opaque. Tags X-ray. So now we have an image that's, we can see where the light bulbs are, we can see where the boards are, and we can see like everything. I didn't remember to transform. That would have been a stupid mistake to catch on camera, but guess what? I didn't. So I'm just going to call this BK Translate. Imagine if I could spell. Panel. Save that, and then I'm also going to go ahead and export this as a PNG, which I can then import into Inkscape. So what I want to do here is I want to route the LED strip so that it goes basically where there were incandescent lights here. I should be over there opening up that LED strip and figuring out what its bend radius is going to be. So that's what I'm going to do. I am just cutting off like 1/8 of an inch off the top, and apparently the bag is resealable so that it doesn't spoil when you have it out of the fridge. Oh, it is very bendy. It is very bendy. I like this. Is it? It's not the best at bending in this direction. It's kind of trying to crease itself a bit. Yeah, it's not actually sealed. It looks like it's like a clear tube almost, and the lights the light strip is just built into it. It expects 12 volts DC, but I'm told it will light at 9, which I'm kind of banking on because we're going to do some interesting stuff to give it a 9-volt power supply. I want to check on what the amperage is. 1.8 amps. So now that makes me wonder, do I have any 1.8 amp power supplies that I could test this thing with? Because I really feel like that would be a good idea. Okay, so this one is 12 volts at half an amp. Not very helpful. 9 volts at even less with a really short cord. Unhelpful. You know, I was thinking because this one was a little bit lighter, maybe it was going to be pretty far off, but this is actually pretty close. This is 12 volts at 1500 milliamps, which is not quite what we wanted, but it's surprisingly close. 7 volts at 400. Oh, you suck. 6 volts at 800. 12 volts at 1000. So far, this has been the best one. Yes, I realize there are more. It's a wire stripper. Why am I not just using the wire stripper functionality? There. Okay, so I'm assuming this on this side is the ground. I should not assume, but my multimeter is not working. Speaking of which, I should probably fix the multimeter. Screen fell out. I just get a new one, but they're freaking expensive and that would be wasteful, so I'm not going to do that. All right, so the red is going to go over here. And the black one is going to go... I already fricked it up. Good enough for a brief test. So I'm going to try that real quick. I'm just going to do it for like a split second. Oh, it's beautiful. That is beautiful. You know, the entire string here is not going to take 1.8 amps. And we can probably measure this and figure out just how much amperage this is going to take. And then we can fuse our circuit for this light specifically. And then if there is a short or whatever, then we don't really have to worry about it because the fuse will actually handle it. If I fold this and then zip tie it down, I can do right angles with this. This would work. The next day I fixed my terrible lighting, put on music-themed Sailor Fugu for some reason, and moved on to the design stage for the plastic framework. For this, I needed to map out the strip layout, determine a mounting method, and reimagine the flasher bulb layout for slightly less depth. This is stupid. This doesn't even match the image that I had in my head, because what I was doing was a spiral. I'm going to redo this. So I'm going to just go over it like this. So over here where I'm marking, that is where our power is going to come in, and then I suppose like right here in the corner is where we can mount our actual power supply, which we are going to design ourselves. Yeah, how do we want to mount this? There's probably a few ways we could do that. Let's do some thinking. Okay, thinking done. I think I know what I'm going to do. I'm going to put blocks on both sides. One over here, one here, one here, one here. And then we'll put pegs or screws in them, or even just T-nuts in the back of them. That could work too. And then we can have little hooks in our piece of plastic here that just goes to the edge, and it can kind of hook into that and then attach. Let's design the hooks, actually. I'm going to have a big circle and then a slightly smaller circle, and then we're just going to, that's not what I wanted to do. We're going to have a rectangle, I don't know why all of this stuff has strokes on it. That's really just making things more complicated. Gonna put that basically there. We're going to put these together, and then I'll drag that down by a tiny bit. And I'll just, I'll group these. Okay, so what we have here is, imagine this being a hole cut out of a piece of plastic. So we have a large circular thing here and then a smaller part. And the idea is there will be a screw that's already here in like a piece of wood behind the plastic. As soon as I fix the orientation, you can drop it down by, I don't know, let's say 1/2 inch, and it will catch in here. And then all you have to do then is tighten the screw. This is not exactly the screw I would want to use. I would want to use a machine screw version of this, which would then mount nicely into a T-nut on the back of the piece of wood. But this is about the same size, and of course we're not going to have it a perfectly snug fit either. We want it to be maybe just a tiny bit bigger. This is a pretty reasonable amount of space I think we can have around our screw. So I'm going to shrink this down until it's roughly the same size. And if it ends up a tiny bit smaller, that's okay, because we gave it a ton of room. Okay, so I realized I can't actually have my plastic go all the way to the edges because I have my backglass guides already attached, and it's going to make it really hard to get the plastic in there, in and out in that case. And this has to be easily removable. Let's see, we'll make this higher. I was holding the... I didn't know you could do that. I literally didn't know you could do that. You can like select a corner thing on here and it'll resize. Okay, that's really interesting. So I'm going to make this semi-transparent so I can see what I'm doing. Let's bring it to like here, because our actual lights are roughly 3/8 inches wide. So I'm also going to make a guide for those. I'm going to make this probably yellow with a width of that's a comma, that's not a point, 0.375. This is going to be the actual size of our lights. Absolutely perfect is not really necessary. The biggest thing that we're trying to do here is we're just trying to have some decent light. So I'm going to make it something like that. Something like that. Because keep in mind, what we're replacing is this randomly placed assortment of individual light bulbs. We're already doing something way, way, way more precise. Okay, so I'm just gonna go ahead and group these, and then I'm gonna copy and paste this 4 times. Well, actually 3 times. I'll put it like here, and then I will flip it horizontally and throw it right there. Good. One kind of funny thing, I played the game not too long ago just because I wanted to see how it was doing. I did decently. I got like 14 million. And I noticed almost every single one of my Backbox insert bulbs is burned out. I'm not even kidding. Like these 2 work, and I think like 1 bulb over here works. Every single other one is burned out. And I looked and the filaments are nowhere to be seen. Either it was burned out or the impact of the machine on the ground finally killed these filaments, but the lights are all bad. So it's going to be a lot more flashy when I'm done with it than it was when I started. I'm going to make my cuts. I will do 1 here I'll make this a dark color so we can see what we're doing. If I put our light over it, maybe I'll make that semi-transparent too. Let's see, how much space are we going to need? About that much. So the idea is I'm not going to cut out everything that is between the lights, because that's just going to make it weaker. So instead what I'm going to do is I'm going to add some cross braces here, just so that we have mostly a solid piece of plastic, but we're still going to have space in the middle here in case we have to do service work on it or something. And then of course we're going to have tons of space on all of these where we can put our zip ties, which I'm going to put, even though the lights have self-adhesive, I want to be absolutely sure they're not going to go anywhere. Actually, I'm going to do something. I'm gonna bring these over like that, and then this one over here I'm going to duplicate to bring to this side, and then that way we're not going to be weakening my material by having too large of areas that are thin, especially thin. So I'll go to like there, go to like there, and I suppose I could just throw this up here as a guideline, and then there are actual guidelines I could be using. I feel dumb I'm not using them. Imagine if I used them. Look at that, an actual guideline. Amazing. If I turn snapping on, then it even attaches nicely. I just said it doesn't have to be precise, and then here I am making it precise. So I've thought it over a little bit. I think our spacing is decent, but one thing that I want to take care of that I didn't really realize thinking about this before is that I need to fix this size. Okay, so this is a much better approximation of the total size. I don't know what I did wrong to screw it up at first, but I'm glad I caught that. So now that that's taken care of, I'm going to correct these. The actual translite, or no, it is a backglass. The actual backglass is going to start how far from the top? I'm going to check that. Just over an inch. So this border that I'm forming here, this is going to be the full visible area, and in fact I'm going to do the same thing down here, and it's just going to be like this much that fits into the U channel at the bottom, or the H channel actually is what it is. Let's add some layers. Move to layer guides. They are moved. Now I can lock this, and now I'm not going to accidentally move these things like I've been doing throughout this entire process. So layer 1 is going to be just our grid. It's funny because grid and guides are both features of Inkscape, and we're not really using either of them. I guess we're using some guides. And then the upper layer is going to be flashers, and then we're going to handle our light bulbs. And for that I'm going to need some sockets. So hang on a second. So this is the socket for a number 89 flash bulb, and that's like these over here, all of these rather large bulbs. They work fine, but the problem is they take a lot of space, and we made our backbox a little bit thinner than the other one, a little bit shallower. And so I don't want there to be any concern about how close we're putting these components to the circuit boards behind them. And so instead we're going to do something else. This is used as an example because I don't have any more of these. I'm going to have to order some. They would be mounted a little bit differently with the tabs sticking out the back. But this is a wedge base light socket, and here is a flasher bulb. This is an LED bulb. I'm not sure whether I'm going to use those or not. I might use standard 906s because there are some issues with putting LED flashers in a System 11 where you can have lights kind of flickering and stuff. And if you fix that, they're still extra bright. And I'm not totally sure I want that because I have played some with LED flashers and they're a bit blinding. So I might do some experimenting, but I'm going to leave myself the space to do experimenting because I'm going to use standard bulb sockets and I'm not going to do any kind of like custom products or anything to replace them. I'm just going to use standard things, standard off-the-shelf stuff that you can get from, in this case, Comet. So what I'm going to do here is I'm going to measure this. Actually, what would make more sense is to look for the actual product. Okay, so this was as I suspected. It was exactly the same as this part, except this base, which might even be able to rotate. Yeah, there we go. That's an excellent way to try this out. So the part here is exactly the same, sticks out to about here. And again, I don't need the exact measurement. I don't need this to be totally perfect. I just need it to be close enough. So 0.625. That is 1/8 of an inch. 0.125 and 0.125. So that is going to be the hole. And what I'm going to do for this, I'm going to group this together. This is basically a side profile flash bulb, like a 906 or whatever this is. So what I'm going to do is I'm going to leave this as it is. That looks so big though. Was I setting radius? Radius. Oh. Well, I'm glad I caught it. What we want to do here is we want to have one of these bulbs wherever there's one of these big bulbs. We could mount these to the back. As in, if I were to put it at like this angle, like that. Hang on, I gotta like rotate it to be like that. Okay, so now we could have a tab sticking out from the main, the frame. Then this bulb could actually be going behind our plastic frame and then just poking out on this side. That might be the best way to do it. I think that might. Then I'm going to copy and paste over to here, and we will do, let's see, something like, no, don't do that. Something like this, and then this. And we might want to adjust these at some point too, because I'm going to have to plan out where the wiring is going to go, and we want to arrange it in a way that's sensible. So now what I'm going to do is I'll take the line tool and I'll see how we're going to wire this up. As far as I know, they're all on one side. I should not assume. I should not assume they're all on one circuit. I just see one orange wire going to all of them. And then a bunch of wires coming back. Okay. I'm going to adjust this one. In fact, I'll delete this, copy this one over here. Then we can have our wires follow here. Or, much more sensibly, I could just bridge across. Instead of having a tab, I'll just have a bridge. I don't remember what color I used, and frankly, I don't care. Nailed it. I will just have a piece of plastic here bridging these across. If we start our wire here, go here, 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 here. I mean, I wasn't actually talking to you, but if you want to be a little lap kitty, you are welcome to do so. Okay, so I'm going to have my wire bend around here, go to this one, and then this one, and then I guess just kind of loop back on itself, and then go along here and cover this, 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 go up here and hit this one, and then hit that one. Make those red, and I'll make it a little bit thicker so we can see what's going on. This could work. I think this would do the trick. As far as I know, they're all wired together as far as power goes. So we only need one wire, which I guess is going to be orange. Going to, well, I mean, I could make the wire orange then. That would make sense. So this will go to all of these lights, and then we'll have individual wires coming back for each of these individual lights. I think this is a fairly clean way of doing it. Although, let's make a tweak here. Let's take this one and rotate it this direction. Yeah, have it right here. Then we don't have to have this weird, stupid little loop back thing going on. We can just mount to there. Imagine my biggest trouble that I'm having is just trying to select. Oh, you know what? This probably has to like get lowered to the bottom. Now I can click on it. Much better. Much better. I'm going to make a new layer actually, and I'm going to call that LED strip. I'm going to go ahead and throw this onto that layer, and then I'm going to make this yellow with a much thicker outline. Maybe I should add some center braces. Plus I need the tabs. I need the tabs for the lights. So let's... what layer did I accidentally throw this on? It is on grid. Okay. Well, I'm just going to copy this. I'll rotate it, and then we'll make smaller ones just for our mounting tabs. I'm going to throw these up here just to have a point to mount the rest of these on. Like I'll have it here because I do know that's going to be important because we're going to have something there. And then this one I'll rotate to the side, and then I'll have a mount point for the beginning of the light string too. And what else do I need? I think that is all. With the physical designs out of the way, it was time to dig into circuits and figuring out a way to power and control the lighting in a way that wouldn't be too jarring. For that, we needed to dig into some electronic concepts. Take it away, Professor Ellie. Alright, so you might be wondering why I have the art program Krita open and not, you know, something electronic. That's because I'm about to talk about some things, I'm about to doodle some things. We've been talking a little bit about how I'm going to do some kind of custom power supply for this game, but I don't think we really specified how that was going to work. So here's how that's going to work. We are using an LED strip. We need a source of 9 volts. Now where on this game are we going to get a source of 9 volts? We've got 5 volts going to at least the power supply, because part of the CPU uses 5 volts. We got 12 volts for the sound system and maybe one other thing, so optos, if it's got any optos, which it does, it's got drive targets. And then it has some higher voltages, like it has 18 for the lamp matrix, it has 25 for low powered coils, and it has 50 for the high power stuff. Oh, and then it has 100 for the display. But there's nothing for 9, at least to my immediate knowledge. What we do get is the actual voltage for the general illumination itself, which is 6.3 volts AC. Now, some of you may be thinking, what does that have to do with anything? And those who are familiar with electronics are probably thinking, oh, wait a minute. Now I'm about to get into a layperson's explanation as to how AC works. If you already understand how that works, I'll probably put a time code that you can skip to. AC essentially means that the electricity is moving backwards and forwards really quickly, typically 60 times a second, unless you live in some countries, in which case it's 50 times a second. And the way we would graph this out is using a sine wave. And this is not a very good sine wave, but and it's not supposed to end like that. It's just because I took my pen off the pad. This is the way we graph out AC. This is a time scale. This point to this point. Well, actually, I'm going to start at 0. So from this point, up, down, and then up again, right there. This is 1/60th of a second from this point until this point. And then the vertical axis here is our voltage level, where the center is no voltage whatsoever. And then up here is a positive, and then down here is a negative. But the thing about having this power not consistently moving is that we're never actually going to reach the maximum voltage, the maximum or minimum, in this case, voltages. It's going to be somewhere down a little bit low. And the best example for this, the numbers, in fact, that I use to calculate everything else, is at least here in the US, we use 120 volt or 117-ish for standard household outlets. And so, you know, you might assume, okay, this up here is 117 volt, and then this is 0, and then this is minus 117. But no, actually, this up here is 170. The maximum voltage that comes out of there is 170. And then, of course, it goes down to negative 170 down here. That might be an approximate. I don't quite know, but it's at least a good start to work with. However, with everything kind of averaging out, because it's going in two directions and there's a certain period of time where there's not really any current flowing at all, it all kind of averages out at 120-ish, 117-ish, whatever. That's a terrible arrow. There we go. And so, given this, if we say that the AC voltage out of the wall is 117, what would happen if we could somehow take all of this power and maximize it? That would essentially mean we would be taking this 117 volts and we would be turning it into 170 volts DC. Now I ran some basic arithmetic calculations and I figured out that 6.3 volts, if we were to convert it in this way without changing anything of the voltage, would turn into just over 9 volts, exactly what we need for the LED strip. Now, before I get too far into designing our circuit that's going to turn this into DC, I would like to specify something. I have not had any formal electronics training, and I'm terrible at mathematics. I am by no means an expert at anything that we're doing here. All of this stuff is already tried and tested by others. Some of it is based on information that I've downloaded or picked up. Some of it I've experimented on my own and come up with things that work. But I should not be considered an expert on how to do electronic engineering. I am mechanical, not electronic engineering. There's a lot more that you could know about for designing, especially we're kind of designing a power supply here. There's a lot of other things that you could do to make it more efficient, to use better components. You know, I'm not necessarily doing things the best way, but I am going to do things in a way that I know works. And for this particular application, I consider that good enough. But I just wanted to throw that little disclaimer in there. Again, I'm not an expert. Do not pretend I am an expert. I am a hobbyist at best. What we're going to do here, I'm going to take out these numbers because we are, of course, going to be turning this into something else. So 9 point, I think it was like 1.5 if I remember the calculation correctly, and then 0 and then minus 9.15. Okay, so how are we going to take this little squiggly line and turn it into a perfectly straight line? Well, the answer is we're not going to make it a perfectly straight line. That is a little bit more complicated than we're able to do. However, we can take a few simple components and put them together, and we're going to make something pretty darn nice anyway. So here's how this is going to work. This is going to be our AC input right here. This will be our 6.3 volts AC coming in, and it's going to come in from two directions. And you might wonder, well, which one is the power, which one's the ground? The answer is neither. AC goes in both directions. Power coming in, we are going to use, I guess we'll use the brown wire because we got to pick one. And I think the other one was white and brown. One of these comes from the wiring harness that goes straight to the game's insert panel and just plugs into a relay that turns the lights on and off. Whereas the other side goes straight into the bulbs, and then it takes a return from the bulbs on the other side going into the relay. And then the relay is driven by one of the solenoid drivers, and when it pulses, it breaks the connection, turns the lights off. Pretty simple. We're going to work without it. I shouldn't have drawn these two lines. I'm just gonna, I'll erase it. I said erase. What are you doing? What is, oh, that's the background. Oh, I'm stupid. I'm drawing on the background. And I call myself a beginner artist. Okay, so I'm just gonna turn this white again. Why am I drawing in pink, by the way? What was I previously drawing in pink? I'm gonna go ahead and sample a color because I already picked pink for some reason, and I guess I'm going to keep doing it. So here is our input at 6.3 volts. What we are going to do is we're going to run it through a device called a bridge rectifier, or in our case, 4 diodes. It's the same function, it's just not in the same package. So this is the way it works. It's typically drawn on a schematic as a diamond shape, but really it can be any formation necessary if we're using individual diodes. Now the function of a diode, if you're not familiar, it's basically a one-way gate. Electricity can go through this direction and not the other direction. The reason why we have this formation going here is when the power is coming through here and it's positive on this side, it can only go one direction, and that's this way. When it goes fully negative, it's going to be going this direction, and it still goes only one way. And these two are going to merge, and I'll explain that in a second. So power is going to go this direction through our devices and then into ground, which is, in this case, just going to be a common reference point, which means this stuff over here is going to eventually connect to this symbol that I drew here very badly. And then we are also going to add another little element here. This is a capacitor. And the function of the capacitor is it's going to smooth out these ripples a little bit. I should be drawing the ripples, actually. I should be graphing this out. If we were to have just one single diode, that one single diode is only going to block the negative voltage. It's not going to do anything for anything else. And so we're going to have these little spaces here. And if we have a device that is going to break if it's hooked up backwards, then yeah, this would save it. But that's not really what we want to do. We want to do a little bit more than that. And so our 4-way bridge rectifier here, these 4 diodes, what this does is when the circuit goes negative, it's still going to allow it through in the same direction. And so instead of these lines here, which I'm going to go ahead and erase, instead it's going to go like that. and we're going to have constant little humps and bumps there. And now you might be looking at this and thinking, okay, but it's still really bumpy looking. We're not going to get the most efficient amount of power here, are we? And you'd be correct. And that's why our capacitor is going to be right here. And the function of the capacitor is, while we have voltage here, it's going to be charging itself up. And when the voltage goes down, it's going to discharge the power that's inside of it back into our circuit. And it's not going to be perfect. It's a very simple AC to DC converter, which means our graph is going to look kind of like this. This would be a lot cleaner if I deleted some stuff, and perhaps I will. This right here is going to be a pretty good conversion from 6.3 volts to roughly 9 volts, and that's going to light our LEDs decently. What's the symbol? I took a second there because I forgot what the symbol was for an LED. It's a diode with I think some little squiggly lines coming off of it. There might be something like that in there anyway. Anyway, this is essentially our circuit. We take our 6.3 volts, we turn it into 9 volts DC, more or less, run it through our LEDs, and then technically we could just run this to ground. But we're not going to do that. See, there's another feature that you may have remembered me mentioning. That's that there's a relay in there for turning the lights off under the power of the computer. And so we might be thinking, oh, well then let's just go ahead and put something like that in there. And yes, this looks terrible, but you get the picture. That is the schematic diagram for a relay. You close the you close the circuit here by, well, actually you open the circuit by charging up this coil right here, makes a little magnetic field, opens up some metal pieces, breaks the circuit. Perfect, we'll just run it through the relay. Well, not so fast, because you might also remember me mentioning LEDs are instant on, instant off. We're going to do something maybe a little bit interesting. We are going to hook up a transistor. And I'm probably screwing up the symbol for this horribly because I don't usually look at this symbol. This right here is a basic setup to do transistor switching. This right here, the component that I'm going to use is an IRL540. Because I'm very familiar with these. I use them for all of these solenoid drivers on both Obsidian High and Undertale. This right here is a 220 ohm resistor. This down, was that 220 or was that 10? This is 10K. This one is 10K. Okay. Here's the way this works. We have a logic signal from the computer, or in this case, something I'll bring up in a second. This is just a current limiting resistor. Otherwise, we put a lot of unnecessary current through our logic system. This is the gate of the transistor right here. If you apply a voltage to this, the transistor turns on and allows current through here. This resistor down here is actually just kind of tying it to ground. That way, if we aren't putting voltage here from our logic device, it doesn't kind of inch its way toward being turned on, even though it's not supposed to. If there's a logic signal coming through here, which is typically going to be about 3.3 volts, then when that reaches this transistor, it's going to allow all of the current from our LEDs to ground, completing the circuit and turning the lights on. This thing right here, how are we going to replace a relay with something that's somehow going to fade these lights in and out like an incandescent bulb? And how the heck are we going to fade when we apparently only get on and off? Lots of good questions here. And the answers to those questions is we're going to use a little piece of magic called the ATtiny85. This is a tiny programmable chip. It's about, oh yay big. We program it to do whatever we want, and then it turns on power for each of these legs depending on what we tell it to do. And so one of those legs will simply be attached to this right here, and I'm also going to specify that one of them is going to go off in another direction where the relay connects to on the driver's side of the relay coil. It's not going to touch the high voltage, it's just going to touch the low. And as long as we have ground connected from the actual backbox itself to this circuit, to the ground on this circuit, then our ATtiny85 is essentially going to be capable of knowing whether or not the relay was turned on or not. And if the relay is turned on, we will shut this light off. If it's turned off, we will turn this light back on. That's the way the original GI circuit works, and it's the way ours will work. And here's the last part of the puzzle, fading on and off like an incandescent bulb. And that is going to use something known as pulse wave modulation, or PWM for short. If you were to take a light switch, don't actually do this, it's stupid and it's probably bad for the components, but if you took a light switch and instead of just turning it on or turning it off, you flicked it on and off really fast, the light would almost seem to be dim. And so this is the way we do it with color changing LEDs, the RGB variety, and all kinds of other stuff. You simply vary the amount of time that the bulb spends on versus off, and then the lights are going to basically do the same thing. And using a little bit of simple math, even though I'm not very good at it, I certainly know how to make a bulb fading script that we can run on the ATtiny. I did the same thing with Obsidian High and it turned out beautifully, so I expect the same results here. I was drawing a graph and I completely forgot. Judging by what I drew here, it's like a 60% duty cycle, but if this happened really super quickly and this was the voltage you applied to a light, it would be dim. It would be like 60% brightness-ish. You might have to experiment with it because there might be either some residual light, there might be some capacitive effects, whatever. It might not be exactly 60% brightness just because nothing is ever perfect, but I think you kind of get the idea how that's going to work. And so with all of that put together, we have our 6.3 volts. We get that turned into 9 volts for our light. We have a computer chip that's going to fade the lights on and off, and we have the transistor that's actually going to be driving it. I said that was the last piece of the puzzle, but I forgot there's one more thing that we have to do, and that's we have to power the computer chip, which runs on 5 volts. Well, actually it runs on, I think it's between 1.3 and 5.5 if I remember the datasheet correctly, but we're going to go with 5 because that's pretty easy. How are we going to do that? The game does have a 5 volt, but it's I think it goes into the CPU, and I already said we weren't going to tap into any of that. Well, we have one more thing that we're going to throw on our circuit board. This voltage regulator right here. This component right here, it kind of just looks like a transistor, but its function is to take a voltage and step it down to something that you want it to be. This variety right here is adjustable, which means depending on the strength of the resistor you throw in here, you can actually adjust the voltage level depending on what you want it to be. You can either hardwire it, or you could put a variable resistor in there and have a physical adjustment on your board that lets you change the voltage. In our case, 5 volts is good enough, and it just happens they have a pretty darn good looking example right here of a voltage converter that'll give us 5 volts. Which I'm going to zoom in a tiny bit on. Apparently this is an improved ripple rejection, which also means this whole rippling thing is going to get a lot better for our logic, which is good because these chips really don't like changing voltages. We're going to take this circuit and we're going to throw it into ours. Like I said, I'm not an electronic expert. I couldn't tell you how they arrived at these precise numbers. I'm going to call them good enough, and I'm going to build the circuit as it is. I probably should study this stuff, but I really don't have time. After I'd finished essentially giving a whiteboard lecture, I fired up the free circuit board design tool, KiCad. The first step of this process was drawing the schematic, and after taking a few moments to relearn it after months of not touching it, I set out to work. Okay, so I'm just going to go ahead and wait for the symbol libraries to load. We will not be able to add an STM32, and I'm not sure why we'd want to. Now we're going to start out with just our power connector, and we're going to need 4 conductors for it. 2 of those are our input power, that's our 6.3 volts AC. One of them is going to go straight to ground, and then one of it is going to go to our power transistor that would normally control the GI on the actual game. Okay, so I'm kind of wondering actually. I thought I could type it. There's literally a search box. Why don't I use the search box? Molex 4-pin. Look at that. I already put it in for my previous project, and it just happens to be exactly the connector that we need. So I'm going to place this. We can actually place things wherever we want on this canvas. We can move things around if necessary. We're probably going to use 1N4004s because I have a ton of these already. So I'm going to place the exact part, and then we don't have to specify it later. We're not going to recreate the exact diamond shape of the bridge rectifier on my sketch. It doesn't really matter what shape it's in as long as it's electrically the same way. Okay, that should do the trick. So what I'm going to do is I'm going to use pins 3 and 4 from this connector for our input. So I'm going to connect these 2, and then this one down here is going to connect to these 2. And then these go like that. One goes over here to the rest of our circuit. Apparently the escape key is not what I want to do there. And then this one goes to here, down by a tiny bit, and then we're going to throw our ground right there. Let's see, which symbol are we going to use? We have ground, and we have ground reference, which is the one I always see on the old schematics, so I'm going to use one that matches. Anything that's marked with the same label, like for example ground, is going to be electrically connected somehow. So whether it's across a grounding plane on the board, or whether we have an actual wire going from here to here, it's going to exist. It's just simplified for the sake of the schematic. C polarized. You know what? I'm going to say that's good enough. I will figure this one out later. I have to figure out later what capacitor I even want to use for this. For right now, this will be good. I just realized from doing my editing of the previous parts, I say we can go ahead and so many freaking times. I did not realize it was one of my speech quirks, but apparently it is. And also saying but I knew that one already. Okay, what's something that's a similar... You know what would be sensible? Just copy it from another design. I'm going to do that. Sure. And now I'm going to zoom in on here. I'm just going to copy these components directly. I don't feel like that's cheating since I placed these in the first place. And let's see if it lets me paste them. Hey, look at that, it does. Add label. This label feature was something that was introduced to me directly as a result of posting a board I had created on Pinside, and a very helpful person who knows more about electronic design than I do pointed out that you can use these. A label makes a connection with a different part of the design, and it lets you specify that things will be connected without drawing a line all the way across, so it makes things less messy. And in fact, it even technically would let you assign one area to one specific function on the board, for instance, and then a different area, like over here, where there happens to be something connected, but you don't need to show it. It makes things a lot cleaner, and I really like the way it looks, especially for the last board that I did, so I'm going to do it again here. This is our input. 3 and 4 is going to be 6.3 volts AC. Go through a bridge rectifier consisting of 4 diodes. Go through a capacitor to smooth everything out. And then from there we have about 9 volts, which is going to go out through this connector into our strip and then back into the driver area, dumping into this transistor right here, which is switched by our driver signal, which has the appropriate resistors in place already. I might clean this up a tiny bit. It doesn't actually look very good. In fact, let's do that right now. Drag here, and then drag here. There. Exactly the same as what we had before, but better looking. Now on the other side, we have one going straight to ground, and then we have one that is going to go to our chip. And I'm going to throw a label on there too. And I'm going to call this signal. Rotate, throw it there. And then we will have a, we'll have an IC. Wait, they have the AT Tiny here? What? Okay, I won't complain. My understanding about this is kind of like the 328, which I've used a whole bunch of times. The reset pin can technically function as a GPIO, but I think you have to do something kind of permanent to the chip in order to make that work. And then it becomes harder to program. So I'm not going to use pin number 5 here. I'm going to just use the rest of them. 9 volts. Perfect. And then I'll also do a label for... can I do like a long label? Can I do a really long label? Oh, you can. I'm going to leave that right there for right now. I promise I will rename it, but that amuses me. I watch Let's Game It Out videos. As far as I know, we only need 2 connections. One for driving the LEDs and one for determining whether they should be on. So 0 and 1 I'm going to leave open for that purpose, and the rest I'm going to specify not being used. Driver, DRV is what I called it earlier. I'm going to put this like here. For this one, it's going to be the sensor. So SIG. That's what I called. Oh, that's not what I wanted. I wanted this. Signal. I'm just going to call it signal. Actually, there's no reason I have to make it all short and cute. That's just going to confuse people. That's like programming and naming your variable X. Which is a stupid idea. It would be like naming a website X. Why would you do that? I think what remains now is going to be the voltage regulator, so I'm going to grab that. So, add. I assume we have this in our library already because it was in the other thing. 1084 CT. I mean, I don't see that one on here. Or 1084 ADG. J. That's a J. That's not a G. Imagine if I understood English. Adjustable output. This is it. This is the part. So I will put this down here. Again, we can move this wherever we want. Stop holding the control key. Now, obviously, I'm going to have to do a little bit of cleaning up here. I still have a label called "Can I do a really long label?" I still have this unconnected thing over here, and I still have a connector I need to put in place. But otherwise, I think our basic concept of the circuit design is pretty much done. I'll go over this off camera, and then we'll cover the next part after that. Once the design process was done, it was time for one of my favorite steps, circuit board design, which worked great, except for one little mistake. Hey guys, check out the circuit board I designed. Because I'm a smart person, and I do smart people things like remember to run the screen recorder while I'm designing a circuit board. 'Cause I'm smart. I should probably keep a tally mark somewhere behind me. Every time I forget to record my screen, I just put a little mark on it as a personal shaming device. Anyway, when we actually left off, I was in the schematic editor, and I don't think it looked like this either. I got everything separated into these nice little boxes here. Our lamp driver circuit is over here, our regulator is here, and I just combined the rectifier and the chip into one because, you know, it's a very simple board in general. There's really no reason why I need to split it up even more than that. So, with this all out of the way, I was able to create my PCB design. I am absolutely going to be designing more circuitry in the future, and hopefully I'll remember to record at that time. But what we have here, it's pretty simple anyway. I'll just give you a tour of what I did, and then we'll be moving on to the next part of the project. So this board is designed to fit into the framework that we designed, which I'm going to even open it up here just to kind of demonstrate it, because I am admittedly proud of this. I exported the board layout in, you know, real life physical units, and I placed it here in my drawing so I can see exactly how big the board has to be and where the mounting holes are supposed to go. So then I added these tabs onto here, which I think turned out nicely. So we have two connectors here, one with the input and the signaling, and then one that goes straight to the lights. We have our voltage regulator circuit over here. We have our actual driver circuit here and our chip that's calling all the shots, and then up here is our rectifier area. Other than that, it's a very simple design, and I go to the 3D view and we have a preview of what it looks like. It does not have the connectors. I'm not sure if I have the 3D models for those or not, or if I'm just like missing them, but I'm not going to worry about that because this is the same setup that I had for my central logic board on Obsidian High, and everything fit together just fine. Before we move on to the display panel repair, I wanted to drop a few of the highlights from the circuit board design video. Much like my Let's Play, it included my own interactions, but I completely forgot to record the screen. Hello. How are you doing? You are moving my mouse cursor. Okay, go do that. Okay, so in the process of waiting for the cat to go through, I was actually distracted long enough that I didn't get suspicious that nothing was happening. So load error, connector HDMI not found. Well, that's a deal breaker, isn't it? You know, all those HDMI ports that I have on my rectifier board, it's not going to work. Okay, so let's see what we actually do need. Some of the assigned footprints are legacy entries with no library names. Would you like KiCad to attempt to convert them? I don't even know if we're using them, but sure, why not? I mean, that seems like a normal resistor size to me. And why would I be looking at options for USB-C extension cables? That's going to be a future video. That is not what I wanted. What if I hold control? Does that, oh, now it works. It didn't work a second ago. I'm sorry, what? Does this not say 220 microfarads? And when I click on it, it says 100. What? It's been kind of ages since I worked on one of these. I'm just going to go ahead and say once again, from top to bottom we get about 69 millimeters. Nice. And then across here, I mean, we could technically go as far as like 87, but I don't think we're going to need that much space. I think we can cram it into an area like this. Would that work? How much wire space do we have? I'm going to look. The answer is we have absolutely nothing to worry about. I can put it wherever I want. Because one side, what does that one side of D3 connect to? Oh, the 9 volt. Oh, I'm stupid. Where do we want this guy to go? Because right up here is where our sensor is. So it would be sensible to have it kind of nearby. There's a missing one. We have 1, 2, and 4. Where's capacitor C3? It's 25. I need to go and find that. Assign footprints 20. Oh, I thought I filled that in. So how big of a hole do we want it to be? So I'm going to place this here. It doesn't need a pad. It's connecting to plastic. It doesn't need a pad. Okay, what did I do? What layer did I throw that on by accident? Hang on, what's going on with this? This is not behaving the way it used to. I'm going to delete you and then I'm going to figure that out in a second. Yeah, here. This is what it's supposed to do. It's supposed to highlight. See, when I click right here to draw a line, to draw a trace, everything else darkens and then it highlights everything that's connected to what I just clicked on. But I do want this thicker. And I think I put that on the wrong layer again. What? Okay. Start here. Then do both of them. And then I gotta draw it. Okay, I got it. I feel like there's something I gotta click on to fill this. Oh, fill all zones. Would have helped if I did that. Okay, now it looks a little better. Now we have a big ground zone here. Okay, so let's see what we missed. Where's the design rules checker? Here we go. Run. What did we mess up? Silk screen overlap doesn't matter. That doesn't matter to me. This, it really doesn't like that being there for some reason. Silk screen clipped by board edge, I don't care. That's it. So it's not saying anything's unconnected. It's not saying I screwed up electrically. It's just complaining a little bit about the silk screen, which I'm not going to worry about. This seems like it's pretty much what I needed. Awesome. So again, I'm going to inspect this before ordering, But this seems like a good, this seems like a pretty good start as far as what we're going to do for our power. And I keep looking at something away from the camera, not the actual camera. I apologize, I had some trouble with my camera and I'm recording from the laptop, which is over there. Perfect. We have our circuit board. Anyway, with all of the orders submitted, I decided to take care of some annoying problems with the display panel, mainly the bottom display hanging forwards and making it difficult to read. From the circular wear patterns on the panel and my own past attempts to remove the display, I knew the issue was related to the T-nuts meant to hold the screws in place. But it took a disassembly to finally paint a picture of what actually failed. Wow, that one's actually surprising me. That one came out. Make a liar out of me. Well, that's 2. 3. Ah, you're the one. Hey, look, broken glass. There's going to be a lot more of that. Told you. You know it would help. Taking this off first. That would help. Ooh, very tight though. Very, very tight. Would not be at all surprised if it was because there was glass stuffed in there. Here we go. I mean, I hate doing this, but it works. It worked. And look, another little piece of glass. How fun. Okay. We're off. I mean, they look okay, actually. Most of them do. That one's missing. That one's entirely missing. I'm going to remove this one. And this one, the spikes look okay. This one, they look okay. It's just this one I got to deal with. And this one, you can tell they're all messed up. Finally out. And so, if we look at this, you can kind of see how the bottom display is kind of sitting forward a little bit, whereas the top one is sitting there nicely. Now we just need to figure out what we're doing with this, and wow, that is some carnage. In the words of Phil Swift, now that's a lot of damage. Ooh, that's a little tight. Or is it the screw? It could be the screw, actually. Let's see if this one goes through. Something's really, really weird. These should just be able to run all the way through. I might just have to buy a whole new set of hardware for these, because these really aren't fitting together the way I'm expecting them to, and that's probably, in fact, the reason why these are all messed up. Yeah, I'm not happy with that at all. If we're going to fix this, let's fix it right. New day, new outlook. First thing you might notice is this tape that I have on here. The reason that's there is to block off this hole. I want to repair this. I'm going to use wood glue for that purpose. I will use the tape now to kind of hold it up on this side, make it level. And then I'll just use some wood glue. Yes, I bought more wood glue, finally. And I'm pretty much just going to squeeze it out And I realize there are probably better ways of doing this, but like everything else in this project, it's good enough. The glue is going to flex a little bit even when it dries. It's not going to be like super strong. And so when we put the T-nut in there, it should sit in nicely. And as long as we do what we're supposed to do with putting the screw in, I think it's going to be okay. Speaking of doing things the right way, I did a little bit of, I guess, shall we say, sleuthing as far as figuring out why this failed in the first place. This was one of the original T-nuts, and this was one of the original screws. I got a whole new set of hardware. If I try to screw this in here, it gets bound up like half... Cat shook the camera. It gets bound up like halfway through that T-nut, and that's as far as it goes. What I figure happened was somebody did some work on this display, possibly trying to fix the problem I'm trying to fix here, and then put it back on, and for each one of these screws, they got bound up. So the person kept trying to turn the screw, and by so doing, took the whole T-nut and just dragged it around in a circle, because you can see where there's kind of circle outlines here. There is one more thing that we can do while we're still waiting for the glue to dry, and that's on this display board right here. I originally tried just pressing this back down onto the adhesive, and well, that was not really good enough, because I checked it out when I came down here today and it had come off again. So what we're going to have to do is we're going to have to deal with some red tape. Admittedly, I don't know what kind of tape this is. It's a double-sided tape. It's about 1/16 of an inch thick, and it's very, very sticky. And it has worked very well for some things that I've done in the past. So I'm pretty confident it's going to work well for fixing the orientation of this display too. So I need to be very careful with this to avoid breaking the legs on this. This one is not coming up as well as the other one did. Oh, spoke too soon. Just had to pull up on it a little bit. Comes right off. That's good. That's very good. And then I'm going to hold this up, and I'm just going to cut 2 strips of this. One goes right there. The other one, try to make the camera able to see this. The other one is going to go right here. Press those down decently. I'm not sure if the camera is going to be able to see this very well, but I am removing the red backing on this side. The heck did I... Ow. Ow. It is a tiny bit thicker than the other one. Just a tiny bit. But I am not going to worry about it. And just double checking all the legs. I think they are okay. Yeah. Okay, I'm going to consider this part fixed. All right, so it hasn't been quite a day yet, but I think that's going to be good enough since we're not exactly going to be stressing this glue. We're just going to put a T-nut down into it. The fact that I used duct tape may make it a little bit difficult to remove. So I'm going to try cutting some away and see where that goes. Okay, I spoke too soon about not getting the tape out. That worked quite well, actually. Now we can put our brand new T-nuts in here. I think I will wait on the gloves till I'm doing something glove-worthy. Now I'm going to push these down into here. Thought that would be a little more of a challenge, but that went in just fine. So I'm going to put this down where it goes. What's going on with this one? Yeah, this is the one that I just glued, and that one's great. This one is giving me trouble, so let's take it out and see what's... It's really stuck, in fact. I know this fit when I bought it. Let me try one of the originals. The original is too big. Never mind. Turns out I had some of these screws already. I didn't really need another one. Okay, this one, I mean, it's a little bit of a rocky start, but it goes in. Which screw was the one? It was this one, because this one's less shiny. Perfect. Now I'm slightly concerned about these screws. They're a bit long. An inch was actually too long. Now I'm sort of seeing a picture forming. I think these screws are supposed to be 7/8 inch at the most, maybe even 3/4, and somebody put screws that are too long, and that might have been part of where this issue started. Screws that are not only too long, but that don't properly fit in the T-nuts. Yep, I think that's what's going on here. I think that is what led to this problem in the first place. Now it should be noted there's a little bit of a spacer underneath this screw, so this washer is not directly touching this trace on the circuit board, although I don't think it necessarily would matter because the screw itself doesn't touch anything else. Good enough. While I had the display panel removed, my eyes landed upon another problem I hadn't previously noticed. One of the speaker wires was cut by a previous owner, then later spliced back together without solder or any kind of insulation. This seems like the type of issue that could lead to disastrous consequences, and I've had enough of those for one game. So I opted to bust out the iron and the heat shrink tubing and give the speaker wiring a much safer and more permanent fix. So this is basically free to flop around anywhere, and if it were to touch something on this board, who knows what would happen. Although given that the display circuit is 100 volts, I'm sure there would be fireworks. So let's fix that. Before I put that together, I have this piece of heat shrink tubing. I'm going to go ahead and cut this to an appropriate size. And I'm going to not forget to put it on. Let's see, I'm going to put it over here. I am going to cut these zip ties off, and I'm going to put some new ones on. I'm going to put more new ones on than old ones I took off, and I'm going to use black, and I think they're going to look very nice. I will twist them in this direction so that it's not just sticking straight out, because that's terrible. I'll grab this thing to kind of hold everything in place. And before I actually touch the solder, I'm going to put my gloves on. There are quite honestly a lot of advantages to using leaded solder, but one of the disadvantages is you don't really want to touch a lot of things with it. Technically, all I would have to do afterwards is wash my hands, make sure I don't touch anything sensitive, but I might as well wear the gloves. There's no reason not to be safe. And now the last thing to do is to put the heat shrink tubing over it. And
what's the best way to hold this? I guess it's gonna be, then you are gonna go here. Unfortunately, this is away from the camera, so we can't see what's going on, but you'll just have to take my word for it. Yeah, honestly, that's not going anywhere, so that's good enough. So here's what I will do. I'm gonna cut off, it's dirty, and this is the hand where I have a display glass wound on my thumb, so I'm going to put this glove on. At least it's possible to wear only one glove. Sometimes I forget that. So I'm going to remove all of these, which I think I told you already. I think I am repeating myself. Now it's time for these. And these we can put at whatever intervals we want. And I'm gonna go with, let's say every 3 inches or so, which is more than there were. We're gonna make this look nice and straight and nice. And then after we're done, after we've pulled all these, then we can cut the ends off and it's gonna look great. Getting the wires straightened out a little bit. Not only does it make it look nicer, it is hopefully going to help keep the wires from getting snagged on things, which does happen on occasion. I would like one of these to land on our heat shrink just to keep it in place. So I'm going to temporarily sacrifice our spacing that I was going with, and I'm going to put it right here. And this one will go directly on it. And I'm going to call that good enough. So then we need only, okay, I'm going to take these off. And I think that looks considerably better than it did. And it's a lot safer, electrically speaking. So with the display taken care of, we're going to put this back together. But before putting the display panel on, I figured I would clean this up first because it is a little bit dirty, and the dirtier it is, the harder it's going to be for that nice bright light to shine through. So I'm going to take some Novus #1 Plastic Clean and Shine. I didn't even have to take the cap off, it just decided to launch itself off, which I suppose could be considered handy. I'm going to spray this a bit. I am not going to replace the light bulbs just yet because I realized I am out of them. Fortunately, I don't have to take the whole panel apart to replace the light bulbs. You can just twist them out because that's the way the wedge-based sockets work. So I'm not going to worry about that right now. I'm just going to put the rest of it back together. Just kind of sit it right there. She's going to be my little helper. There we go. There we go. It's just a bit tight. That one in there, like that. This one, there's a grounding wire going from the speaker body to this panel right here. That's one. That's two. That's three. That's four, and I bet I kind of obscured all those with my hand from the camera, and I'm so sorry I messed up. This is a little bit loose. I'm going to tighten that. That was not a pleasant sound, if we're being honest. That goes in. Anything else loose? I think the speakers are okay. I think we're good. We are indeed good. Now, I put in several orders: electronics, custom plastics, and the new circuit board. And so far, the electronics are all I've gotten so far. So rather than drag this video on even longer than it already has, I'll be splitting off the assembly and testing process into a part 3, and I hope you'll join me for that. Good night, everybody.